Imagine for a moment the sound, the low-frequency shaking rumble of 6 million cubic feet of water crashing down every single minute. For centuries, Niagara Falls has stood as the ultimate symbol of nature's power. It is an icon of immutability. Every year, millions of us flock to the edge of the Horseshoe Falls. We stand at the precipice, mesmerized by the mist and the thunder, believing we are looking at something eternal. To the casual observer, and truthfully, even to geologists for generations, Niagara has represented a predictable force. We thought we knew its story. We thought we understood its timeline. It was a textbook example of a slow, steady march upstream, carving a path through the landscape over thousands of years. The mechanics seem simple. Water wears away rock, a process as old as the Earth itself. But, Ari, we were wrong. A groundbreaking scientific investigation has recently shattered this illusion of predictability. Hidden beneath those roaring waters, buried deep under millions of tons of concrete infrastructure, lies a secret. It is a geological secret that challenges 12,000 years of assumptions. Recent seismic imaging, combined with advanced fiber-optic sensing, has revealed something startling. There is a dense, interconnected network of deep fractures extending up to 200 meters, that's over 650 feet, straight down into the bedrock beneath the river. These aren't just surface cracks from erosion. This is a systemic structural web. It is a discovery that compromises the very foundation of the falls. Today, we are shifting the narrative. So we are moving from a story of manageable surface erosion to one of potential structural instability. And this raises urgent questions. Is the natural wonder safe? And perhaps more critically, what about the massive hydroelectric plants that power the lives of millions nearby? This is the story of the silent fractures. Part 1. The Geological Legacy. To truly understand why this new discovery is so alarming, we first need to look at what we thought we knew. We need to look at the textbook model of Niagara Falls. Let's rewind the clock. The story begins approximately 12,000 years ago at the violent end of the last ice age. As the massive Wisconsin glaciers retreated, torrents of meltwater needed a path to the sea. They carved through the landscape, creating the Niagara Escarpment. Over these millennia, and while the falls have been on a journey, they haven't stood still. They have retreated nearly 10 kilometers from their original location, moving upstream to where they are today. Now here is the science of how that happens. The stability of Niagara relies on a very specific layer cake of geology. The top layer, the riverbed you would walk on if the water dried up, is composed of Lockport dolostone. This is a hard-resistant magnesium limestone. It's tough. It's the shield. Directly beneath this protective caprock lies the Rochester Shale. This is a much softer, layered sedimentary rock. Historically, we viewed erosion here as a bottom-up process. Step 1. The turbulent water at the base of the falls smashes into that soft shale, eating it away. Step 2. This leaves the hard dolostone caprock unsupported. It hangs over the edge like a heavy shelf with no brackets. Step 3. Gravity wins. The caprock snaps under its own weight and collapses into the gorge in massive blocks. That is how the falls retreat. It's a cycle of undercut, collapse, and repeat. In the 19th century, this retreat was happening fast, about 1.5 meters every single year. But then came the 20th century, and with it, the era of human engineering. We decided to harness the river. By building massive diversion tunnels for the Sir Adam Beck plant in Canada and the Robert Moses plant in the USA, engineers sucked huge volumes of water away from the falls to generate electricity. This had a side effect: preservation. With less water crashing down, erosion slowed to a crawl, less than 0.5 meter per year at the Horseshoe Falls. For decades, we patted ourselves on the back. This engineered balance seemed perfect. We believed we had tamed the geological clock. But the new data suggests that while we may have slowed the surface, we missed a deeper, darker process occurring within the Earth itself. Part 2. The discovery of the fracture network. The complacency regarding Niagara's bedrock ended recently. It began with the deployment of next-generation seismic imaging technologies. What was supposed to be a routine checkup of the riverbed turned into a revelation. Previous surveys had always seen cracks. Of course, there are cracks. The rock endures freezing winters in the crushing weight of water. But those were surface fissures. They were considered normal. This time, researchers probed deeper. Using seismic nodes capable of listening to the Earth deep underground, they discovered that the bedrock is not a solid, monolithic block. Instead, it is riddled with a dense, interconnected fracture network. And I want to emphasize the depth here. These fractures go down 200 meters. This led to the active reworking hypothesis. These fractures cut through everything, the hard dolostone cap and the soft shale beneath. And critically, they aren't isolated cracks. They form a web. This suggests the bedrock is undergoing active reworking. The earth beneath the river is shifting, settling, and cracking in response to stress in ways that surface observations never predicted. This finding upends the theory that undercutting is the only thing we need to worry about. We now know the foundation itself is compromised. The falls aren't just eroding from the face backward, they are potentially fragmenting from the bottom up. Part 3. Into the Abyss. The Field Investigation. Confirming these ghostly seismic images required a daring physical investigation. This part of the story reads less like a science experiment and more like a high-stakes expedition. Teams of experts, geologists, and structural engineers had to descend into the gorge, directly beneath the pounding mist of the falls. Picture the environment. It is hostile. You are facing blinding water spray. The falling water generates unpredictable, hurricane-force winds, and there is the constant, looming threat of loose rock falling from the canyon walls above you. In these conditions, they deployed a piece of technology that acts as the nervous system of the rock, or they use fiber-optic sensing technology. Now, traditional sensors only measure movement at a single point, but a fiber-optic cable, it acts as a continuous sensor along its entire length. Here is how it works. The cables are sensitive to microscopic strains. If the rock shifts even a fraction of a millimeter, it stretches or compresses the light pulses traveling inside the glass cable. This streams real-time data on stress, vibration, and temperature directly to surface computers. To make sense of this data, they built a digital twin. They combined the fiber optic data with ground-penetrating radar, or GPR. This allows them to see cross-sections of the Earth. When they fed all this numbers into the computer, they created a 3D model of the subsurface, and what they saw was concerning. In the model, in the areas of high stress glow red, and the model didn't just show random red spots, it revealed clusters, alarming concentrations of fractures. And these clusters weren't just anywhere. They were concentrated near critical infrastructure zones, specifically near the hydroelectric intake tunnels. Part 4. Infrastructure at the Brink. This is where the conversation shifts from geological curiosity to public safety. The Niagara River is the heartbeat of the region's power grid. The infrastructure built to harness it sits directly on top of this fractured foundation. We are talking about the Sir Adam Beck Complex in Ontario and the Robert Moses Niagara Power Plant in New York. Together, they serve nearly 4 million people. These facilities rely on massive intake tunnels that run beneath the cities and the riverbed to funnel water to the turbines. The new 3D models show that these tunnels, and even some control rooms, intersect with the newly identified fracture zones. Consider the physics of this. During peak operation, the flow volume exceeds 2,000 cubic meters per second. The hydraulic pressure exerted by this moving water is immense. There is a phenomenon known as hydraulic jacking. If water under that kind of pressure finds a crack in the bedrock surrounding a tunnel, it forces its way in. It acts like a wedge, driving the crack open further. Engineers have already noted a sign. There is a slight but statistically significant increase in tunnel seepage. Water is leaking in. While authorities say it is currently within historical norms, in the context of this new discovery, that seepage is a potential red flag. It could indicate that the fracture network is expanding. Part 5. Simulating the future. So what happens next? With the 3D map in hand, researchers are running advanced simulations. They are trying to predict how the bedrock will behave. Because we don't know exactly how fast the fractures are growing, scientists have to deal in probabilities. Two primary scenarios have emerged. Scenario A is the slow transformation. In this version of the future, the fracture network behaves plastically. Water pressure and the yearly freeze-thaw cycles gradually widen the cracks over decades. The outcome? We see manageable erosion, small rockfalls, minor shifts. This is the best-case scenario. It allows for mitigation. Engineers can reinforce tunnels with steel liners. They can inject grout into the fractures to glue them back together. They can plan for the future. But then there is Scenario B, rapid failure. This is the black swan event that keeps engineers awake at night. In this scenario, a trigger event occurs. Maybe it's a sudden surge in river pressure, like the massive ice jams of 1954. Maybe it's a minor earthquake, or maybe it's just the material fatigue of the rock finally giving up. The result? The fracture network connects instantaneously. Instead of small rocks falling, massive sections of the riverbed could collapse at once. If this happens near an intake tunnel, it could breach the system, flooding control rooms. If it happens near the lip of the falls, it could radically alter the shape of the cataract in seconds. And here is the sobering truth. Comparative studies of similar geological formations elsewhere in the world suggest that both scenarios are plausible. Nature has a history of moving very slowly and then moving very, very fast. Part 6. Guardians of the Gorge. This sounds frightening, but it is important to know that we are not helpless. Recognizing that the bedrock is less stable than believed, authorities have shifted their strategy. They have moved from passive observation to active defense. The management of Niagara Falls is a binational responsibility, overseen by the International Niagara Control Board. In response to this data, the falls are now under 24/7 electronic surveillance. The sensor suite has been expanded. It now includes seismic nodes, pressure transducers, and permanent fiber-optic lines embedded in the rock. Data is not stored for later review. It is processed in real time. If a sensor detects a strain anomaly, a sudden, unexplained shift, alarms are triggered immediately for review by geologists. There is also a commitment to transparency. In an age of digital misinformation, rumors of Niagara collapsing can spread faster than the cracks themselves. The scientific team is publishing daily summaries. They are making raw data available to the global research community. The goal is to balance caution with calm. Decisions must be based on evidence, not fear. Furthermore, emergency preparedness has evolved. Canadian and American agencies now conduct joint emergency drills for the rapid failure scenario. These aren't just paper drills. One where they simulate rapid shutdown protocols for the plants to reduce pressure on the rock. They practice evacuation plans for the tourist zones. They are integrating sensor alerts with regional emergency notification systems. Conclusion: a new era of understanding. The discovery of the deep fracture network beneath Niagara Falls marks a definitive turning point. We can no longer view the falls as a static monument. We can no longer view its erosion as a simple surface calculation found in a high school textbook. The falls have been revealed as a dynamic, shifting entity. It is fighting a battle against gravity and water pressure deep within its own foundation. The implications are profound. For the engineers at Sir Adam Beck and Robert Moses, the bedrock is no longer a solid anchor, but a variable to be managed. If for the scientific community, it is a humble reminder that even the most studied landscapes harbor secrets. And for us, the public, it underscores the fragility of the natural world. Two futures lie ahead: a slow transformation or a sudden reshaping. But through advanced technology, international cooperation, and vigilant monitoring, humanity is doing its best to prepare for both. The roar of Niagara continues, but now we are listening more closely than ever to the whispers in the stone beneath.